Okay, so today again our speaker is Tekin Karadağ, and he will be giving talk on Lie structure on Hochschild and Hopf algebra homology.
So last week I told a little bit about the structure on Hochschild homology and Hopf algebra. And this week I will basically calculate the bracket structure on Hopf algebra homology and Hochschild homology of a Taft algebra. And I will tell you why I take Taft algebra. So it's going to be starting of my talk. So I will give some equation and then some definition in Hochschild homology and Hopf algebra. And then I will try to calculate bracket structure on Hochschild homology of Taft algebra. And then I will give the relation between Hopf algebra homology and Hochschild homology. And lastly, I will give the bracket of Hopf algebra homology. Okay, Gerstenhaber and Schaaf conjectured in that Hopf algebra homology. I wrote here G structure, and by G structure I mean there is a cup product which gives the algebra associativity, and there is a Gerstenhaber product. Which gives the algebra relativity. The conjecture is solved in 2002 in physical paper. One is from Tekin and the other from Algebra. And they show that Hopf algebra has a G structure, and they also show that Hopf algebra, the G structure, the bracket structure, Hopf algebra homology is trivial when the Hopf algebra is quasi-triangular. And then in 2016, Herman looked at a more general perspective, and he showed that this structure is trivial if the category is trivial. And in fact, if Hopf algebra is quasi-triangular, then the category is going to be graded. The category that we invested is going to be graded. So it's going to be kind of special case. Herman generalized the result of Hernani and Polodar and Algebra. And natural question again is like, what is the bracket structure on Hopf algebra homology when Hopf algebra is a non-quasi-triangular Hopf algebra? Okay, here some definition in Hochschild homology. So let's say A be a field, A be a K algebra, then we define enveloping algebra by A to the E equals A times A opposite. And here A opposite is the multiplication with A opposite is given by A opposite multiplication is just E times A. So the multiplication on the enveloping algebra is just A1 times A1 A2 tensor into B1. And then we can construct the chain complex, and the chain complex is just the n minus 1 to the n equals 0. So we can construct this chain complex. We can just take the tensor power of A, and then with the differential here, that's going to be a chain complex, and it's called bar complex. And A free the K algebra, so this bar complex is going to be the resolution of A unit to A. So that's the resolution of bar resolution. And what is the Cauchy homology? We apply Hom to bar resolution, this Hom to bar resolution, and then we get a leaf resolution here. And differentials are given by these dns are f equals f, and dns are differential resolution. So the Cauchy homology is defined in this way. It is just a sum of the map of over image of the previous map. Okay, here the calculation for Cauchy homology when the algebra is the truncated polynomial algebra. So in here we take the field with characteristic 0 and the algebra is direct over x and ideal geometry from x to the t. And then that resolution is exact if we define U map as x tensor 1 minus 1 tensor x and V map as follows. So if you look up this, I mean, we will hear about this resolution when we try to calculate the bracket structure on top of like Cauchy homology. So we apply forms to this resolution to find Cauchy homology. And once we apply forms, each term is going to be form a to the e, a to the a, but it is isomorphic. So the isomorphic resolution is going to be the first term is going to be a, the first term is a here, so that's going to be a, and the second, I mean, each term is going to be because each term in the resolution is e, and the max person is 0 in positive, and 2 times x to the minus 1 is even. And if we calculate Cauchy homology for this resolution, then we have Cauchy homology is a in degree 0, and it is just ideal generated of x in positive and ideal generated a over ideal generated by x to the minus 1 in even. And Cauchy homology direct double. We have two structures on Cauchy homology, cup product and Gerstenhaber bracket. And we define cup product on chain level. So we get a map on degree m and a map on degree n, and then cup product will give you a map on degree m plus n. And we also define Gerstenhaber bracket on degree, like with the element in degree m and element in degree n, and the bracket is going to be then element in degree m plus n. And with these two structures, Cauchy homology is a Gerstenhaber algebra. So, and one thing that makes Cauchy homology Gerstenhaber algebra because cup product is compatible with Gerstenhaber bracket, and the meaning of this is if you have alpha, beta, cup, gamma, then it is alpha, beta, cup, gamma, plus some minus 1 to the some degree, depending on the element, times b cup alpha gamma. So with that compatibility, we call Cauchy homology is a Gerstenhaber algebra. Okay. I want you to focus on for Gerstenhaber bracket formula for a second. So bracket is defined by circle product minus the reversal. And if you look up circle product with simply define on by resolution. So That's why we want to calculate the bracket, if possible. We want to calculate bracket from some different resolutions. So that is our main reason of calculating bracket with the bar resolution is not easy. And we have a technique given by Negron and Witherspoon in 2018. And it says, let's say we have a resolution which satisfies some condition which I don't want to do with the detail. And let's say see the contracting homotopy for math as A, and I will give details in the next slide about that homotopy. Then the bracket is given by this formula. So this is the P bracket, and it is pretty similar bracket with the original definition, but the circle products are allowed easy to calculate. So for circle product, what we need, we have element F, element G. So we need P map and we need the element. By the way, here delta 2 is just delta is cohomologization. And delta 2 is just delta tensor 1 or 1 tensor delta. And that bracket agrees with the Gerstenhaber bracket. So what we are going to do, we will find a resolution which satisfies the condition, and we will find the contracting homotopy for the map as A, which I will find in the next slide. And then if we find also diagonal map, then we will be able to find the bracket structure on Hochschild problem. Okay, here is the resolution that I have in the example. And that resolution is my equal. Oh, I didn't define it yet. I didn't define it yet. And so I gave the definition here. So I didn't want to make it part of that piece, but yeah, so the definition here. And it's just the chain map defined by mu tensor. I mean, you can think of it as a modification. Mu tensor identity on resolution minus identity on resolution. What do you like to say? Mu is just like you can think of it as a modification. So this is generally the way we define mu. So you take the resolution and you, and this method is generally mu is 0 on all others. So that's why we have is 0 on higher. It is just defined. Yeah, augmentation. Yeah. So now these are the steps. What we are going to do, we want to find the chain map P, but we cannot find chain map P for this. I'm sorry, we cannot find the contracting homotopy P for this map dimension. So we want to find contracting homotopy for identity map first. And then we just, the next step, we try to find contracting homotopy for this chain map. And by contracting homotopy for this chain map, I mean it should satisfy. So that is the technique. So if I find H, I will find P inductively. We take P minus 0 and bracket in higher degree. And lastly, we will find the diagonal map, And if we find those, then we will apply the formula in the previous theorem, and we will start to find the bracket structure from Hochschild formula. Okay, I didn't include H, P, and delta, but but I can drag you to the math. But okay, let's say we find the math. Now what we are going to do, we need to find the bracket function for lowest degree element, like the one and two. And because of the compatibility, we can just construct the higher. So we are just wondering what is the bracket structure in the one and two element, the one and two element, and the two and two element. Then we will use the compatibility and find the higher degree. Okay. So remember all the terms in this resolution is just a to the e, which is under the algebra. But it was isomorphic to that. It was originally this one is, I take this one as a generator. On each degree, and let's notate it with psi I or I, and then let's say XA psi I part is the element that conjugate which sends the generator to X to the G. Then once we calculate the brackets for degree 1 and degree 1 element will be the first time, bracket in degree 1 and degree 12, second time, and bracket in degree 2 and degree 12. And this is pretty similar calculation with the article written by Negron and Witherspoon, but in there they took the characteristic of scale positive, and in here we are doing the calculation with characteristic of field 0. And next we will somehow relate Hochschild formula to four. But let me remind you the definition of four again. So let's say we have an algebra over a field, and it is a Hopf algebra if it has four algebra structures. With that, I mean it should have four multiplication, four units, and unfold. And it should satisfy these three conditions. The easiest example to Hopf algebras is group algebra. So if you think about group algebra, with this four multiplication and the four units and the unfold, it gives the Hopf algebra structure. But I will not be clear about Taft algebra because they are not quasi-triangular. I will mention that. I will mention about the definition in a couple of slides. So let's define Taft algebra here. Let's say P is greater than or equal to 2, and TP is a K algebra generated by P and X. And the relations are given by G to the P equals 1, X to the P equals 0, and XG equals WGS. And W omega here is just and with this four multiplication, with 4 units and the transport, the Taft algebra is Hopf algebra. Actually, it is a non-commutative Hopf algebra, and what do I mean with that? When you apply existing math to co-multiplication, you need to have co-multiplication again, where tau is just existing math, so it is from A tensor A to A tensor A, and then X tensor Y to Y. So this is co-commutativity. and it's half algebra, non-cohomology. One question. Yeah. So you remember cohomology? I thought the cohomology yeah, I think we just I mean, yeah, I am not checking. But yeah, I think that matters. All right. So what is the key group algebra? Let it be a finite group acting on the algebra A by automorphism. Then key group algebra is a vector space that A tends directly to G is just vector space A and G. But multiplication is given from one, so you do not multiply the first term directly with the line. But the G1 vector on E2. So when G1 passes to G2, it should have on the first like and you have the regular multiplication for G1, G2. And you can see Taft algebra as a Q algebra. So at Taft algebra you can see as A is just KF over equity, and G is just cycle with order T. And we have action G action and only again. So I gave a definition of quasi-triangular algebra. But there are some other definitions which relate quasi-triangular algebra. So if we have a Hopf algebra, then let's define R as sum of A1 sample equals that is a function. And we define R1, R12, R13, and R23 as in this way. Then we say A is quadriangular if two were to actually. And in 2003, Council of Order gave a proof that a Taft algebra is a non-quadriangular if how is the yeah. And yeah, if I need to say that if Hopf algebra is cohomologies, that means how then it is automatically quadriangular. That the equations are satisfied. So if you are looking for non-quasi-triangular Hopf algebra, you need to check for like non-cohomologies Hopf algebra. Yeah, that I mean, just for you just pick it up. That on R we have got something. Yeah, one I mean, if you can, that's one of them should be. In this group, in group of as far as I remember, she went through like three categories, and I mean, I can give actually maybe more. No, I'm just yeah. You pick one invertible element. Yes. Yes. I mean, if R is any invertible element on A tensor A, then that's or any R. Yeah, or any R. And this I mean, this is not pretty similar definition, but in some, like in category theory, some people they define quasi-triangular algebra as if you have M and N as a module, they say just M tensor N should be functorial isomorphic to M tensor N. Yeah, this is kind of yeah, kind of. I mean, it should be. Yeah, it should be kind of like you can say yeah. Yeah, it should be kind of. All right. So now I will try to calculate cohomology. So we take the same, we start with the same resolution, and now we will apply T to the T tensor B from both sides, I mean from left side. So we just write TP. And what is B here? B is the Steven algebra. And remember, we can see TP from the previous slide. We can see TP as a TP. So we are finding this resolution first. I will not write differential here. So this is just TP tensor over B, A to the E, TP tensor over B. So we have it, and now what we do, we use this isomorphism. Actually, the isomorphism is not straightforward, so there is an isomorphism between these two, and should be composition to this isomorphism. But we have this isomorphism. So if we have that TP to the a to the e, what we try to do, I will not, it's going to be a little sketchy here, but you can see a to the e as a tensor a as a vector space. So that is going to be isomorphic for EP tensor a, and that's going to be isomorphic for a tensor b. So finally, this resolution turns into a tilde, and each term is going to be a tensor. And the last term is going to be just into so that applies to I mean, to apply to I put that here. And the last term is going to be just so this is the resolution of T now. And this map, actually the map here is the same defined in this way. And both maps work, so we take if you want to find 3 tilde, we just these tensor identity to G. Because this again, this one you can see as a tensor AG. Remember the scheme group algebra was a vector a tensor. So we can see this term as a tensor G. And on a tensor A, we define B, and we just cancel by identity map. And that map works. And with these maps now, we do the same process. We try to calculate H tilde, E tilde, and delta tilde for this resolution. And we also, I mean, I didn't write here, but yes, there is a lemma that also says H tilde is a compact homomorphic for that. And P is a compact homomorphic for f of a for this. And delta tilde is the comma. So we will apply the same technique, but again, I mean, because of the isomorphism, we need to turn back and take the elements from the form group, and then we need to find the with the isomorphism, we need to find the bracket structure. So there is an isomorphism in between G invariant of PT and this form group. And G invariant of PT is spanned by 1 to GT, 1 G to G to the P minus 1 in given degree, and just multiply by X on the left and into the span size in all degree. And then we just use the isomorphism here, and then we take the corresponding map in form group in even and in form group. The form group from all degrees for these are the and F theta, the definition of F theta is given here. So if you apply isomorphism to the elements and get elements in form group, then you will understand it. So now we will calculate the bracket structure on the tilde map. So if we calculate bracket structure with tilde map, then in degree 1 and degree 1 elements, we have 0. In degree 1 and degree 2 elements, we have this bracket. And in degree 2 and degree 2 elements, we have the again have. And this calculation is different now from what I mentioned. So if we change the characteristic of field from positive characteristic to 0, then this bracket for degree 1 and degree 2 elements, it changes also. The last thing that I do is I will try to embed cohomology in Hochschild and try to find the corresponding bracket of cohomology. What is the cohomology? Cohomology is defined as x of xk on the top of that. So there is a theorem that cohomology is a Gerstenhaber algebra, which we mentioned at the beginning. It is proven in 2002. And also, if is any quasi-triangular algebra, then the bracket starts at 0. It is also 2002. And here's another theorem from Kumar from 1993 that if we have any algebra with projective 1 to 4, then we can embed algebra cohomology into the Hochschild form. And I want to mention about the restrictions here. So, algebra cohomology with projective 1 to 4 is not so restrictive because algebra, like all finite dimensional algebra, have projective 1 to 4, and almost all known infinite dimensional algebras also have projective 1 to 4. So that condition is not so restrictive for us. Yeah, I mean, you can write what you from the problem. So that's one. You find it somehow. This statement follows. Oh yeah. It comes from either one. Yeah. I mean, oh, but wait, at that time, we didn't know this because we didn't know that because of the form. And yeah, that can be another. Yeah. 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 Yeah, in the control role, yeah, you have it. You can say this and then okay. So yeah, I mean, what there can be done, you use and you so this calculation was done by 1 million in 2013. She calculated the cohomology of Taft, and then we try to talk to the whole body. And as you see here, if there is an embedding, it should be identical and even, and it should be just zero. So for Hochschild cohomology, if we want to find the bracket structure, the bracket structure should exist on degree 2 and degree 2 elements, and we can access them. But if you remember, let me remind you the bracket structure on Hochschild cohomology. So for degree 2 and degree 2 elements, the bracket structure is down. So for Hochschild cohomology, for even degree elements, the bracket structure should be down. So that's why we can take the next theorem actually. So graded Lie algebra structure of top algebra cohomology of a top algebra is available. In fact, we do not have any all the elements and even zero on and why this is important? Because it is the first calculation of bracket structure on all parts of the problem because non-quasi-triangular. And of course, we want to extend the result, and results actually extended with a different technique, or can be it can be another presentation here, another slide. So yeah, I finished a little early, so thank you for listening. Like for compound, okay, here it is. So I guess the answer is right. So you take the L on, and then so the tail end is yeah, yeah. So this and yeah, I mean for that case, yeah, you can say that I'm not sure. That's yeah, I mean you can take KS. But yeah, and that case, I think for the function formula to come part of what from the so you can extend without a but here.
Okay, anything else? Then let's thank the speaker again.